Guys, I think you're still muted.
Yeah, sorry about that. I don't think you need to start again, but just keep going.
I don't think you missed anything. So, cool. Can you hear us now?
Yes, we can. Thank you.
Okay, fantastic. Great. So yeah, so variational inference is kind of like an obvious task, or it's sort of a well-known task that normalizing flows are used for. Another task is density estimation. Density estimation, roughly speaking, you could say is the task of determining the density of some, say, IID sample, perhaps under some assumptions that it lives in some family of densities. I'm going to talk about both of these. And the sort of high-level idea behind normalizing flows is to essentially, there are ways to use neural networks to parameterize families of diffeomorphisms that can then be used to obtain densities for both of these applications via the change of variables formula. We'll see a little bit more about that in a second. Use the trick again. Cool. Great. So how does this work? So yeah, as I said, the idea is to use is to parameterize a family of diffeomorphisms and then to choose a fixed noise distribution PZ. And the idea is that the diffeomorphism induces a density by the change of variables formula. So essentially, you can consider the sort of model expressed by normalizing flow for a fixed set of parameters to be the marginal here in W of this generative process. So you sample from your noise distribution, and then you map that sample through your diffeomorphism. You can kind of view that, if you want to sort of zoom out and think kind of like distributionally, it's sort of like continuous kind of deformation of some noise through this invertible function. And the cool thing about that is that, you know, assuming that you have a diffeomorphism, you get a nice expression for the density of the marginal in W. It's given by the change of variables formula there. So this here denotes the Jacobian evaluated at W. Right. So that's kind of the high level. Let's talk a little bit more about how that can be used in variational inference in particular. Yeah, these slides were sort of made for another session. I think you all know what variational inference is by now. Very briefly, you have some joint distribution, you want to obtain a posterior. We're going to use, we're going to try and minimize some divergence. In this case, I'm just going to purely focus on KL. From some family of densities that you parameterize this fixed posterior distribution that you have sort of already set up. And I guess one thing that's sort of implicit when you want to do this is that if you want to do this well, it's clear that you need to obtain an expressive family of distributions. Otherwise, if you go away and do this minimization problem, the resulting minimum of that KL will still be large. If you don't have a very expressive family and you've got a complicated posterior here, like the best you can do won't be particularly good, and you end up sort of far away from the thing that you actually care about. So really, you want to make sure that you've got a very large sort of, or ideally not very large, you want it to be very expressive. Ideally, it would just be a really small family containing just the posterior. But if you don't know what that is, you want to sort of make sure that you've chosen a family of densities that's large enough that it will contain something that looks kind of like the posterior, so that when you actually do this minimization problem, you end up getting something that looks pretty good. And that's really what normalizing flows are all about. They're about ways to sort of, or at least when used for variational inference, there are ways to parameterize expressive families that, you know, hopefully improves your performance in this respect. Okay, so let's think about like how you could actually parameterize such a family. A sort of natural thing to do, and it was done historically a lot, is mean field. So mean field basically says, okay, I want to parameterize this joint distribution here over Y here is going to be a vector. So what I could do is basically just posit sort of independent marginals for each dimension of Y. And I'll, you know, that induces sort of a factorization of this family like so. And it's kind of natural to use, I guess, a Gaussian as each of those factors as well. So mean field Gaussian is often kind of, this is mean field Gaussian. I guess mean field by itself would typically just mean that you're making sort of an independent assumption. We heard earlier about variational autoencoders. Essentially, this is what a VAE is doing, actually. It's doing it in a slightly more complicated way because Y here will depend on X. See up here, this is kind of, I'm imagining that I'm doing variational inference like one shot. So I'm only doing it once for a specific value of X, but you could imagine if you did this for different values of X, that I could make these values of mu and sigma depend on X. That's essentially what the variational autoencoder is actually doing. So it's really a mean field Gaussian approximation. Posterior distribution that you get comes out to be essentially this normal here. So yeah, I guess I should have kind of emphasized this a bit more. If you do this kind of for each component, it's clear that what you get overall when you sort of take the product is you get something that's Gaussian as well. It's going to have a mean given by the individual means of those Gaussians, and it's going to have a diagonal covariance matrix where each dimension is scaled by the corresponding value of sigma I that you've chosen. And yeah, so just to stress again, a variational autoencoder is essentially going to have this as the posterior, but like these are going to be neural nets that take X as input. And that's essentially the only difference. So this is quite a common thing, or it was a common thing to do. And it works well in some contexts, but it's kind of clear that that's also not super expressive. Obtain like a really complicated posterior. Mainly because you can kind of see this intuitively that for one thing, it's unimodal, right? So you can't have, two modes as a Gaussian. A lot of posteriors are not unimodal, so that's already kind of a problem. And on top of that, it's axis aligned. So there's a diagonal covariance matrix. So you can scale sort of the individual covariances, but you can't rotate the covariance to kind of follow the pattern of noise in some way if there's correlations. So it's clear that this isn't kind of what you want to do. So how can we do better? I guess, so I'm also falling into the trap of only citing the 2015 paper.
That's what you say.
So there is indeed other work, which I also cite. This paper by Razende Mohammed, which was sort of the first one to kind of really bring this at least to the machine learning community. Essentially, the idea behind this work is to use normalizing flows to obtain sort of a more expressive family of posterior distributions. And so, as I sort of said earlier, they take Q phi, this family of posteriors, to be the marginal distribution of Y obtained by this generative process. And you can kind of get a sense just intuitively that this is going to help because, here are this is a figure taken from their paper, basically just looking at before training, I think, if you parameterize a normalizing flow in this way and you sort of look at the density that you get, what does it look like? These are two different families that they consider. These are clearly not unimodal or axis aligned. So it's clear that you're sort of getting more expressiveness in your family of posteriors than you had with a mean field approximation. So that's kind of, that bodes well. Okay, this is the derivation for the elbow. You don't need to see this again, I'm sure. I guess, yeah, that's the elbow. I guess the key point is that you still want to optimize that. We're doing variational inference here. So we need a way to optimize that elbow for this particular choice of model where we've got this diffeomorphism in there. And I guess the idea here is really just to use the fact that Q phi is obtained essentially as a push forward, literally the push forward of the distribution of Z by F phi. So essentially you can kind of, it's the law of the unconscious statistician again. Similarly, as for the reparameterization trick, you can kind of just bring this integral, which is expressed in terms of it's averaging over Q phi. You can turn that into an average over PZ and bring the resulting value in like that. If you want to optimize this, you need a gradient. How can you do that? well, you can differentiate under the integral sign. Sorry, is that
Just aiming the camera at you.
okay? Great. So yeah, you need a gradient to do optimization. We're trying to learn the parameters of this model. So how do you do that? You can differentiate under the integral sign like so, assuming that that works, but in practice, everyone just assumes that that's okay. And you can see here, because this PZ term doesn't depend on the parameters of the model, that essentially, if you sample from Z and then compute the resulting value of this guy, so you've got a Z random variable and you compute that guy there, that's an unbiased estimate of this gradient term. So suddenly you have unbiased estimates of a gradient. You can use that in an optimization pipeline to learn the parameters phi here in this way. Is that kind of clear to everyone? That's kind of the main idea behind normalizing flows. So great. So let's summarize that. So for variational inference, the idea is, in practice, what you need to do is you need to choose a noise distribution and you need to parameterize a family of these diffeomorphisms. We'll talk a bit more about how you can actually do that later. To train the model, you will sample from your noise distribution and you will compute this gradient here using autodiff. And then that gives you an unbiased estimate of the gradient of the elbow with respect to these parameters. And you can update those parameters using stochastic gradient ascent. And you can learn your expressive posterior, which is great. Cool. So that's sort of the high level. In practice, typically, perhaps even exclusively, people use neural nets for F5. It's really sort of point of this is to try and find ways to bring kind of the expressiveness of neural nets to bear on this problem. You can actually also use a normalizing, you can actually also use neural nets in PZ, provided, so that's actually what Representative Mohammed did, is they had sort of a kind of standard mean field VAE posterior to begin with, and then they sort of put a normalizing flow on top. And that's okay too, provided essentially you can do the same thing here, where you can kind of outsource, where you can kind of do the law of the unconscious statistician, and you can, the reparameterization trick, whatever you want to call it, and sort of get to this point here as well. So maybe you would have like P epsilon there instead of PZ, if you're kind of familiar with that. But yeah, the point is, so you'd use a neural net in F and potentially PZ. You compute your gradients via autodiff. In order to make this work in practice, you need to be able to sample efficiently from Q5. So remember how we're doing this. We are computing gradients here by, well, first of all, we're basically sampling from Q5 here. So we're sort of sampling from PZ and then we're mapping it through F5. That's the same thing as sampling from Q5. So you need to be able to do that efficiently if this is going to be a productive way to train your model. But you don't need to be able to compute. So the point basically here is that you only need to be able to compute this efficiently in one direction. So you need to be able to compute F5Z, but you don't need to be able to compute the inverse of Y. And the reason for that is because the only densities that you need to be able to compute correspond to the densities evaluated at points whose inverse you already know because you sampled them. I'm not sure if that's entirely clear to everyone. In general, you might want to be able to compute Q phi of Y for an arbitrary value of Y. So you don't know which Z mapped to Y. Obviously, there's only a unique one because this is a diffeomorphism. So if you want to compute Q phi of Y for an arbitrary value of Y, you first of all have to figure out which Z mapped to it, and then you get the Q phi value. The point here is that for variational inference, you don't need to be able to do that because you've sampled that value of Y essentially by sampling Z and mapping it through FZ. So obviously you kind of know the inverse of this guy. It's sort of where you started. So the point is essentially you only need to be able to do this efficiently in one direction. That's kind of a theme of normalizing flows. We'll see in density estimation if that's the case as well. Cool, and you can amortize this procedure as well. I won't talk too much about that, but essentially if you want to make this depend on Z, depend on X, you can. That's fine. Great, so that's variational inference. The other application, as I said, is density estimation. that people use normalizing flows for. To kind of recap what this is. So essentially the idea is you have some samples, X1 through N, let's say they're IID. They come from some unknown data generating distribution. And you want to figure out like, what is that distribution? That's a, hilariously ill-posed problem. But, maybe you can think that sort of under some assumptions, sort of on smoothness or regularity or something, you can kind of do something here. And it's clear that there are sort of interesting applications if you could, such as, for example, out of distribution detection. That's a little bit controversial. People have found that actually some of these high dimensional density estimators don't really do what you would expect for kind of out of distribution detection. But ostensibly, if you have a density and you find a point has sort of low density, then you sort of know it's a bit anomalous in some sense. Another application is synthetic data generation. So you might want to do this if you want to kind of like augment a data set for some other training procedure that you're considering, for example. But yeah, let's just take this as a problem that you're interested in. An illustrative approach to how you can do density estimation is, of course, kernel density estimation. The idea here is that you basically take your data, which in this figure here are these points just living on the x-axis. And the idea is to basically just put a scaled Gaussian on top of each one and essentially take the average of those. So you're putting a little Gaussian on each one, you get overall like something that looks like this, and it sort of seems sensible enough to do, and it looks all right in this picture here. The problem with that is the curse of dimensionality. So essentially, with this Gaussian case, you're sort of relying on an L2 distance, which, as we know, kind of breaks down in high dimensions. It's a sort of bad way for expressing distances when you've got lots of flexibility in terms of how you move around the space. So different strategies than this are needed. And I guess, again, the intuition behind using normalizing flows for this is that, well, neural nets have done really well for high dimensional problems, like classification, for example. Can this be used in some way to do density estimation? How can you actually construct a density using a neural net? It's not necessarily an obvious task. But normalizing flows are a way to do this. So here's kind of how it works. The idea is essentially now to basically, it's quite similar in some ways to variational inference, except that we're looking at a KL divergence here where the order is reversed. I'll explain why that needs to happen in a second. The idea is you have your unknown data distribution P data, and you consider sort of projecting it onto this family of densities that you have parameterized. And as with variational inference, it's kind of clear that you need to parameterize a quite expressive family of P thetas in order for this to make sense. Otherwise, you're going to end up with something, if you do this minimization problem, you're going to end up with something that's actually quite far away from the real data that you care about. Of course, if you go too far, you'll end up with deltas on everything. So sort of a little bit of an art, but that's the idea.
Just one question about
Yeah.
this. Maybe you're going to explain it as well. But the KL is kind of undefined if the support's mismatch, right? So your data is going to be discretely supported, presumably P theta is continuous.
Yeah, so let's assume for simplicity, everyone in this literature just assumes P data is supported on the whole space. So let's say everything is strictly positive density.
So how do you compute the KL then?
Well, yeah, we'll see that next slide. And the topic of supports is actually a very apt one. Or the point of supports is a very apt one. I'll talk more about that later as well. That's quite an interesting. Normalizing flows interact quite interestingly with supports, as we'll see. Yeah. So okay, great. So yeah, again, here's the idea. How do you parameterize a density with a neural net? It's not obvious. The idea here is to take again your density model to be the marginal distribution of this generative process. So you sample again from some noise distribution, you map it through your diffeomorphism, and you get some random variable x out whose marginal corresponds to the density that you are parameterizing. And this gives the procedure clearly for sampling from P theta. You can sort of run this forward. You can sample your Z in map it through F, and you get a sample from X, or a sample of X, basically. And you can also compute densities, again, via the change of variables. So that's something you might want to do in a density estimation problem. You might want to be able to, I guess for the out of distribution detection kind of scenario that I mentioned before that you might want to consider using this for, have a number that tells you whether you are high density or low density. That's a useful thing, and you can get that with normalizing flow in this way. And yeah, the point of normalizing flows is that this will often be constructed in such a way that it's tractable. It kind of looks crazy, right? Like a determinant of a Jacobian, it's like a large, X is potentially a very large dimensional vector. How can that possibly be tractable? We're going to see in a second kind of how you can do that. Okay, so how do you train these models? Let's say you have a family of densities parameterized in this way. How do you kind of learn the parameters theta here in some way? And this is the reason that, this is basically why you don't need to know P data, because essentially what you do is you, again, differentiate under the integral sign and kind of just hope for the best. And what happens is that there's a term P data of this KL divergence that doesn't depend on theta. So essentially, if you're allowed to do this, which everyone assumes, again, that you can see here that this gradient doesn't depend, like, assuming you have the ability to sample from P data, you can get unbiased estimates of this thing here without actually knowing the value of P data. You just need to be able to get samples from it. Because all you need to be able to optimize this thing is an unbiased estimate of the gradient here. So that's great. So we have this. We can sample from the data and then compute this gradient here via autodiff or whatever. And then we can optimize this thing via stochastic gradient descent. Cool. So here's the summary. So for density estimation, it's quite similar in some ways to variational inference. The idea is you will start by choosing your noise distribution, PZ, and you will parameterize your family of diffeomorphisms. You'll sample from the data generating distribution and you'll compute this this gradient here, and then you'll update your parameter theta via stochastic gradient descent. And that will give you, that's basically a methodology for sort of learning these parameters. Theta, it's sort of a kind of correct optimization procedure in some sense. Again, in practice, you want to use a neural net to parameterize F theta because it's sort of more expressiveness. And you definitely want to compute this gradient via autodiff. You don't want to be doing that by hand, but that's fine. It's very easy to do these days. As before, you only need to be able to do this efficiently in one direction. You only need to be able to sort of compute the normalizing flow in one direction. So essentially what that means, so in this case here, we need to be able to compute F inverse. I give you a value of X. I need to be able to compute, technically, I just need the gradient of the log. I don't necessarily need this thing itself. But if you want to compute a density, you need to be able to compute that term there. So one direction you need to know, the other direction you don't. It's clear sort of from this optimization procedure here, you actually don't need the ability to sample from this density model in order to train it. We just need the ability to compute these gradients, essentially compute these densities and then backpropagate through it, essentially.
But ultimately, for generative modeling, you do want to sample from P theta, right?
It depends. So if your goal is generative modeling, for sure. If you're just interested in out of distribution detection, for example, then you might be willing to kind of compromise with that. Another point to note here is that I say efficiently. So often what will happen in some of these architectures, and we'll see some examples later, is that you'll be able to go in both directions, but one direction will be a lot quicker than the other. So training time, you sort of can't use the slow direction, but at test time, if you want to sample a point, you can, it's just a bit slower. Great. Any questions so far?
So for the density estimation part, I know that there is no reparameterization trick. There is nothing you can do. You have the P data that's already at high value.
Yeah, definitely. So we're just relying on samples from the data, and then essentially that's all you need. So you don't, exactly. It's a much simpler derivation than the elbow, in the case of the elbow. And actually, a point to note here is I'm being a little bit sly. I mean, in practice, people don't do it like this, where they, technically, if you wanted unbiased estimates, you would sample a fresh data point at each iteration, right? You would never reuse the same data point. If you have a sort of finite data set, you would never reuse the same data point. You would only have, you would only be allowed to make sort of one pass through your data. In practice, everyone makes many passes, and it's fine. But this kind of maybe gives you a flavor of why this is a sensible thing to do. Technically, if you're doing that, if you're making many passes over your data, let's say you're sampling uniformly at random, then you do have an ill-posed KL problem, because the thing that you're optimizing to is actually an empirical distribution, but it's fine in practice. Cool. Okay. So how do we actually, so that's what you would use a normalizing flow for. How do you actually obtain a family of normalizing flows? So how do you obtain a family of diffeomorphisms, I guess, more precisely? That's basically what I'm going to talk about now. So there's sort of two key requirements that you need. You need this thing to be invertible, obviously. You don't necessarily need that to be explicitly invertible. You might not actually know the inverse, but you need to construct it in such a way that you'll guarantee that the inverse exists. And you need there to be a tractable log Jacobian. So we saw that here in the case of density estimation. It was the case earlier for variational as well. So you need this term here to somehow be tractable in some way that you can at least use it, in this case, to get log or gradients of the log density. Right, and I think a point to mention that I won't necessarily dwell on is that I'm going to sort of describe kind of primitive flow steps. So kind of 1F, but you can, as was mentioned, you can compose these things to obtain sort of more expressiveness. So let's say you have sort of one layer of diffeomorphism that has these properties. You sort of stack them on top of each other, you obtain something that still has these properties, and you can kind of work with, but potentially gives you more expressiveness because there's kind of more complexity in that function that you've parameterized. But I'm just going to really talk about sort of one sort of primitive flow step, and then kind of build up very easily from there. Okay, so here is a classic normalizing flow. It's called real NVP. Essentially what it does is we're parameterizing, so this needs to be a diffeomorphism. So it's taking a d-dimensional vector as input W. And what it does is it passes the first d dimensions through unchanged, so 1 through little d. And then it uses these first dimensions to obtain the transformation here on the remaining dimensions. Notice that so S and T here are neural nets, let's say. They're completely unconstrained. They can be really any function that you want. That's where the parameters of this model kind of come into play. So those neural nets only depend on the first D parameters, which went through unchanged. And then the transformation, the dependence of the remaining dimensions on these first dimensions is quite simple. Once they're sort of mapped through, it's this very simple affine transformation of the remaining layers. Essentially, you pass these things through unchanged, you put them into neural nets, and then you use that in this affine way to obtain this overall function here. I wrote on the slide, it's clear that it's invertible. It's probably not clear, actually, but it is the case. So the reason it's invertible is if I give you a value in the output space here, so you certainly know which dimensions, which values of these guys sort of achieve that value that you've hit. And then you can use that, you can map them through to sort of obtain S and T. And this thing here is clearly invertible once you know the values of those terms. So essentially you would subtract off this and then you divide by that, which is positive. So given a value in the output space, you can figure out the value W that maps to that original term. Is that kind of clear to everyone? That's sort of the main idea.
Assuming we know sign everything from the neural network, that's all fixed.
Yeah, exactly. So you've chosen those, you have full access to them, and yeah, exactly. Cool. The other thing that this has, it's invertible. It needs a tractable logic over it. How does it get that? Well, essentially,
1 second. So I sent two different neural networks. So two different.
it can be, yeah, absolutely, yeah.
Oh, okay. I somehow expected them to have different parameters.
Oh, so there's no requirement that these be the same parameters.
Yeah.
So yeah, it could, yeah, exactly. I mean, it could be that the first half of the psi parameters go.
Yeah.
So the first, so the choice of the function, the affine function, right, is arbitrary to a point. You could do something else potentially. So for the invertible, for the fact of being invertible.
Yeah.
But is it a problem for, is the only choice that has tractable Jacobians? Or?
So I'm going to give another example that isn't based on this architecture that is still tractable. It's less, conveniently tractable in a sense, as we'll see, but yeah.
I was just pointing like those earlier works that are not cited, actually they designed those invertible transformation using like PCAs, ICAs, all these sort of like simple like linear algebra application before neural networks. But like, yeah, so you don't even need neural network to kind of get those.
Yeah, absolutely. This could be literally like a linear function of like T and S can be linear, like if you want to. This was kind of, I guess, an advantage of this. I mean, so basically the context for this paper, real MVP, is like, it was the first normalizing flow paper for density estimation I'm aware of that really kind of scaled the architecture. So they managed to build a really big density model with this kind of architecture. I think because it's quite simple, it sort of scales better in a sense. Everything's affine and S and T. They're just sort of simple neural nets. So you just kind of pass things through and you get a result. On the next slide, we'll see that that's not the case for in all cases, but I think essentially that was the motivation. And the idea is that, I guess, if you do this enough times, essentially what you're doing in an individual layer is sort of less relevant perhaps than like you've got like 100 layers of this thing. And
This was the first coupling architecture, I guess.
I think so, yeah.
I think I can remember. I was trying to remember if there's something before. Yeah,
I think there was another one by Din et al. What's it
I
called?
think this was the paper with Kingma, right? The Kingma was there. I think 1:1 coupling one. I think this one the thing. Yeah.
Yeah, but I think there's one. I'll try and find it afterwards.
This one is super popular.
Yeah, exactly. Yeah. This made this put normalizing flows on the map, I guess. Yeah. So I had a question.
I think the one with the same authors around the same time was nice.
Yes. Yeah. That's it. Yeah. I guess had a less catchy name than real MVP. Didn't make them as famous, but anyway, cool. So that's great. One thing actually to note, I didn't really mention this, but it kind of gets to the question of like what you're allowed to do at each layer. It's like, obviously, so these first D dimensions are going through unchanged. So if you wanted to like get an expressive density out of this, you would certainly need to compose multiple of these. And you would need to also make sure that you're alternating which dimensions go through unchanged and which dimensions go through this bit here, which are not unchanged. It's sort of clear intuitively, if you just stacked 100 of these layers through, just exactly like this, even if you're using a different neural net at each layer, like these first 3 dimensions aren't touched. So you kind of in a bit of trouble. So what they did in this paper is to basically alternate which dimensions are transformed and which dimensions are not. And that was enough. And another point to note actually as well, which is also somewhat interesting and peculiar, is that like this doesn't work for one-dimensional densities. So that's kind of a bit strange, like 2-dimensional plus family of densities, but there it is. Cool. Okay, yeah, and I guess the last point is that this is hopefully relatively clear that it's got a lower triangular Jacobian. The reason being, well, the Jacobian for this part is going to be the identity. And then each of these remaining dimensions here only depend on the stuff before it. So WD plus 1 only depends on W1 up to D, and similarly, upwards. So you get a lower triangular Jacobian, so it's tractable, it's the product of the diagonals, and you can get a closed form formula, which is nice. Great. Here's a slightly more, I guess this is the king of the paper. So this is a slightly more complicated example, similar idea. Instead of having this kind of block diagonal form, the idea is essentially to do this affine trick at each layer. So essentially, for the first layer, this is empty. So essentially, you just do sort of an affine transformation on your first W1. And then for the remaining layers here, like you map the previous dimensions through unconstrained neural nets, and then you do an affine transformation of your dimension. And it's clear again by the same argument that if I sort of tell you the value in the output space, you can kind of work backwards, starting from the first dimension and using the fact that you know these neural nets to figure out sort of what the inverse is. And again, because everything only depends on the previous dimensions, you've got a lower triangular Jacobian as well. One thing about this that's potentially less desirable is that if you notice here, if we actually use, so this one here used one neural net, S and T, or two neural nets, I guess, but essentially one pass through a neural net. So you take your D dimensions and you pass that through these guys, and you get the result. Here we're using separate neural nets, and then the output, well, I guess, yeah, we're using separate neural nets per dimensions. If you're doing all of this sort of in different passes through a neural net, that's potentially very inefficient. But one innovation that was made, no pun intended, was made, and essentially what this did is essentially to parameterize the neural net in such a way that you can sort of pass all of your W's through the neural net and ensure that each output only depended on sort of the previous stuff. So it uses a kind of binary masking strategy inside the neural net to make sure that you can still use a single S and T up here, and you can map everything through it, and you get all your outputs W, or I guess the transformations of W. They're order, but they're guaranteed to have this sort of order regressive property, which gives you all the nice things that you care about for your normalizing flow. So that's and it was used for variational inference and also density estimation in these two papers here as well. Last normalizing flow architecture I'll talk about. This is just to give you a flavor sort of for what's possible, and this is quite a different architecture, I would say. Is called residual flows. So residual flows basically are motivated by the observation that so these two models here, real MVP, and these models based on MADE, they have a tractable Jacobian because it's lower triangular, which is good for trackability, but in a sense, it's kind of bad for expressiveness because I guess intuitively it seems like having a lower triangular Jacobian kind of restricts what the model can kind of do. That's really the sort of motivation, at least. It's not a very precise statement, but it's perhaps intuitively okay. So the idea of this paper, residual flows, is basically to parameterize a normalizing flow in this way, where basically you sort of have your W that goes in, and then you add W some function G that you enforce the condition that it has to be Lipschitz with a constant less than 1. And why does that give even an invertible function? You can kind of see in the 1D case, if this were 1D, so you got two functions here, you got W and this Lipschitz guy here. This is like the real line, let's say. So in every unit interval, or every interval of any length, this part here increases by a length of 1, or the length of the interval. And this thing here, by construction, can't change by more than 1. So overall, there's no, this thing is guaranteed to be monotonic. Essentially, that's the idea. So, this part always increases by the length of the interval, and this part can't decrease by that same length. So overall, their sum is guaranteed to be increasing, therefore invertible. The idea essentially then scales to higher dimensions as well. How do you make a neural net have this property? That's a bit more challenging than I guess these earlier architectures. The strategy that these guys use is spectral normalization. So the idea is essentially, if you imagine just sort of at test time, if you have a neural net, and you go through and you compute the largest singular values for each linear layer in the neural net, you sort of divide through by that. You can then show that will ensure that each linear layer has a Lipschitz constant less than 1. And then you use non-linearities in the neural net that also are guaranteed to have a Lipschitz constant less than 1 just by construction. You can use like a ReLU. Does everyone know what a ReLU is? So you can use a ReLU with a gradient less than 1, for example. So you're composing things that all have, well, actually, if you make sure that the linear layers have a gradient of, or a Lipschitz constant of less than 1, you could actually use a ReLU with a Lipschitz constant of equal to 1, but it's fine. So that's the idea. Essentially, is they call it spectral normalization. How do you compute the Jacobian of this? Well, it turns out you can write the log Jacobian as an infinite series, a matrix power series, I guess. And you can use debiasing techniques based on Russian roulette sampling, if you're familiar with that. Plus the Skilling Hutchinson trace estimator, which these guys really made famous through a couple of papers, including this one. And you can get at least an unbiased estimate of the log Jacobian, which is enough to do training. Great. This won't necessarily have a tractable inverse either. You can sort of see that, like we've essentially just specified this in one direction. G here is a neural net. But, it's not clear how you would go backwards. You can actually do so using essentially an iterative algorithm based on the Banach fixed point theorem, turns out. You don't need that at training time, but at test time, perhaps you might for various reasons. Great, okay, we're nearly at the end. So this is essentially some work that I worked on during my PhD that kind of engages with some of this, particularly, I guess, in the density estimation case, although we did some follow-up work as well on variational inference, kind of looking at sort of limitations of normalizing flows and some ideas to potentially improve them. And I guess the motivating intuition behind this is that everything we've talked about is based on diffeomorphisms, right? So that's a quite strong condition. In particular, what a diffeomorphism does is it preserves the topology of the input that it takes, or the space that it is defined on. So what that means, intuitively, is that it will preserve the number of connected components, the number of holes, and sort of how the input space is knotted, and so on and so on. So this is some quite complicated, potentially invariants that are sort of guaranteed to be preserved if you parameterize a model in this way. And intuitively, what that suggests is that if you use a normalizing flow, so you take some noise Z and you map it through a diffeomorphism, then essentially the support that Z lives on will be at least topologically equivalent to the support that the eventual X lives on as well, intuitively speaking. What we show more precisely is that if this isn't the case, because I guess you might be willing to sort of, let's say that the support is not homeomorphic to the support of the data, the support of your noise distribution, that is. It turns out that a sequence of diffeomorphisms Fn can only yield a good approximation in distribution sense for the data if the Lipschitz constant of either the forward direction or the inverse direction of that neural net, the normalizing flow, goes to infinity. So we call this the bi-Lipschitz constant of that normalizing flow. This is a very general result, like we're not making any assumptions at all on the architecture or anything like that. It's just diffeomorphisms. It wasn't trivial to show. Yeah, the proof is in the paper. There might be a simpler way to do it. Perhaps someone has an idea.
I missed it. What does N stand for here? The number of.
Yeah, so I'm basically just saying like, okay, N is sort of like a hypothetical sequence of diffeomorphisms that you have that we're sort of imagining are getting closer to some, in some ways.
Yeah, sorry.
Exactly.
Do you have this for like conditional distribution also? Like if I'm conditioning on like to like, product space and then going forward, like, I think so, maybe. Intuition is that same would be valid. So like if I have holes or not holes, one of them, maybe I'm having Z and Y and then passing back and transforming, keeping Y the same, but transforming the Z to X. So I get a X given Y.
Yeah.
But I think the same would, my intuition is the same would apply there as well.
Yeah, if by conditional you mean like we're going to put some other term in Fn, it's going to be diffeomorphism for every fixed value of that, then yeah, it would definitely apply. Essentially all flows have this property, which is kind of interesting. What does that mean in practice? So actually, I guess just to mention this is quite a strong, so the support being homeomorphic is quite a strong constraint. In practice, as I mentioned earlier, you might be willing to assume that your data lives on the whole space with at least negligible but positive probability. And perhaps you've chosen PZ such that that's the case as well. If it's a Gaussian, that's certainly true. In that case, the supports are homeomorphic. So does this still apply? Well, not exactly, but approximately. And the reason is quite simple, because this is convergence in distribution. Essentially, what it means is that like, if your data distribution is close to something in distribution sense that is not homeomorphic to your noise distribution, then essentially you still have to get some sort of blow up happening as you go to infinity. So, if the data is sort of mostly kind of living on a set that's not homeomorphic, essentially the same problem arises as well. So it's not something that just happens because we've made this kind of strong assumption about the supports being like exactly not homeomorphic or strictly not homeomorphic. Okay, cool. So yeah, as I said, this applies more generally than this applies like absolutely in general, like to all normalizing flows. An immediate consequence you can kind of see from this is that anytime you've got sort of blow up like convergence infinity, something's going to go wrong numerically. And indeed, that is what happens. So it's actually observed by Bergman et al. That essentially, if you want to find kind of, if you look for it in the right way, you will find regions of a normalizing flow where they're actually numerically not invertible, essentially because this bi-Lipschitz constant is blowing up. So either you have a region where the normalizing flow has to jump very quickly, or you have a region where it's very flat and close to sort of zero gradients, it's not invertible. So that's kind of like an immediate consequence for all flows. But it also applies to residual flows as well, in particular, I guess. Residual flows, remember, with this architecture based on this Lipschitz neural net, this neural net with a bounded Lipschitz constant. So this here is kind of like illustrating what happens. So here we've got data living like where these dots are, and we're trying to learn that density. And I don't know if it's clear, I'm hoping it's visible, but you can sort of see like there's mass being, this is a residual flow that's been trained. It's a really big model. It's been trained to completion, etc. It's placing mass obviously in the regions where there's data. But if you can also see, it's also smearing out like a little bit of mass like in between. And here it kind of can't like you can't quite bring all the mass out, essentially, for a similar reason. I mean, the point here is that, it's not just that there are two connected components in the left-hand side, and our noise distribution only has one. This is a situation where you've actually got one connected component, but obviously it's not homeomorphic to what we started with. You get the same problem happening there. Just can't quite bring that mass out. And that's exactly what this result predicts, because essentially you can show by the construction of a residual flow, which has this Lipschitz neural net involved in it, that it actually can't achieve this. So the Lipschitz constant, the bi-Lipschitz constant of a residual flow by construction is actually bounded. So if it's bounded, then you can't have convergence in distribution if the supports aren't homeomorphic. So it's kind of like a fundamental limit on the expressiveness of the model that you get. I think it's kind of nice that you can actually really see that visually in these examples as well. We sort of thought about this a little bit and kind of proposed a potential way to mitigate this. The idea is basically to think about replacing this sort of standard flow-based architecture, which sort of considers a single diffeomorphism with a family of diffeomorphisms, essentially. So imagine now that for each value of u, you've got a separate normalizing flow f. That there is the normalizing flow. Just that guy is a normalizing flow for every value of u. And so the idea is kind of like, similarly to before we have this noise distribution we sample from, then we use that noise distribution to obtain an index, sort of this u value, which actually determines which flow we're going to use. And then from that, we obtain like our x in the way that we did previously. Is that relatively clear? Cool. You can do this, like, I guess one of the nice things about this is that any normalizing flow can be used to construct f in this way. So essentially, if you imagine that's f is just a standard normalizing flow that you define, you can do essentially kind of same affine trick that we had previously, where you make that depend on the u. Now you've got a function that's in u is clearly invertible because essentially this part is, and sorry, in z is invertible for every value of u because this part is and f is by construction. But it has this kind of greater expressiveness where like different values of u kind of give you a different normalizing flow if you consider it kind of as a whole thing rather than just like the normalizing flow here is more than just the f basically.
Sorry, I'm a bit confused. So earlier when you had, I think it was real MVP, right? The neural networks had fixed parameters, fixed parameters, right?
Yeah.
And now for each index variable u that you sample, are those u variables, they're not used as parameters, just used to.
Yeah, they're the inputs. So I guess, yeah, I've hidden
the inputs, but then the parameters, are they still shared across?
They could be, yeah. So, I mean, they needn't be. I think in our experiments, what we did was we just had separate S and T, like there were independent networks, basically. I've hidden the phi. I had phi or psi previously. There should be a kind of semicolon psi there. But yeah, it's hidden there secretly. F, it's the same as well. It also has some parameters, and all of this you would learn using gradient descent.
Thank you so much.
Yeah, so we really wanted this to be kind of like it's not really changing the ideas behind flows, it's just kind of like augmenting them in a certain way. So it turns out, and it's relatively clear, you can stack this architecture and you can obtain more expressiveness in just the same way as you stack a normalizing flow, or you compose a normalizing flow with other flows, and you obtain a more complicated flow. So it's a similar kind of deal here. Essentially, it's looking at kind of this L-step generative process where you sample from some noise distribution, and then at each stage you sample an index, which gives you the flow that you want to use. Then you map your noise through that flow, and you get essentially a kind of new noise distribution to pass through the rest of the model in this way. What you sacrifice with this is that unlike normalizing flows, which are tractable by construction, your PX is going to be typically your marginal in X is going to be intractable. The reason for that is essentially that you don't know sort of which flow gave you which value, basically, intuitively speaking. But the joint turns out to have a closed form, because basically, if I tell you the value of U, the index, then you do know which flow you used. It was the flow corresponding to the value of U. So essentially, we can, if someone's interested, you can come and find me and we can talk about this. Essentially, it's just like the same. If that term were not there, or if for example, let's say the U space were a singleton set, so this is just one, then we're back to like normalizing flow density that we started with. That's basically the idea. It's kind of a generalization where this extra term is sort of providing like the weight according to which index you. Right, so we don't have a closed form for the marginal, we have a closed form for the joint, so we can actually still train this model. Guess what with variational inference, right? So I told you that was going to be anyway. Yeah, so you can posit an inference model QU, which is like an approximate posterior, and this here should hopefully be familiar to you all by now. This is essentially an elbow, where this is the approximate posterior, and we are maximizing this thing, which is the lower bound, to the log probability, and so it provides a way, essentially in the same way that you train a VAE, you can train one of these models as well. And then, a lot of people complain about like loose tractability. Oh, that's, normalizing flows are all about tractability, but it's not really so bad, because at test time, if you need to actually compute a density, like where you really care about the number, you can still obtain that basically by using, I don't know if you talked about I-way at some stage, essentially using I-way, like you can kind of do, this is sort of one important sample, you can do like many important samples in there, and you can have that thing.
I-way is expensive. You pay some extra computation.
But you're at test time, so it's like, all right, it's fine. Yeah, the point is, if you really cared about it, you could get the numerical. Like,
but without using I-way, I mean, like, won't you get a good bound without using I-way? I mean, like, you have tested, like.
So for training, it's absolutely this.
You still have stable training without I-way.
Yeah, exactly. For training, I think everything we did was one sample.
One sample is open, right?
Yeah, literally. But I guess the point is just that you don't sacrifice, in a sense, you don't sacrifice like numerical tractability of the marginal. You sacrifice kind of like exact tractability, but I think that's a bit overrated, to be honest. And you can get all the precision you ever want in this way if you really need it. That's, yeah. At training time, I agree, it's not such a great idea,
but I mean, like, there's always compromise. So, like,
yeah,
if you think you have like separated modes with, then obviously there is limitation of, so you gain something and you do.
Yeah, 100%. Yeah, it's never win-win, as much as we claimed so in the paper. But
that's the whole point of the workshop. Otherwise, we have been doing MC anyway.
Yeah. Yeah. Okay. So we need a Q. So we need a choice of Q. Right. You've now seen. You've learned about variational inference for a couple of days now. So you know essentially different ways to do this. One way to do this would be essentially just to like directly parameterize a sort of expressive Q, perhaps using a normalizing flow even, right? Like you could literally use a flow to obtain a model over those guys there, those LU terms. But there's more structure in this model than that. So that would kind of be a waste, because essentially what you can show is that the posterior distribution, if you imagine sort of sampling from the posterior distribution, that corresponds to a generative process that basically has this form, where these are actually, if you imagine that these are actually the posteriors of U given Z. So yeah, I don't know if that really makes sense. The point here is that you only need to parameterize this part of the posterior. You don't want to parameterize like a full posterior over all of the U's. You don't want to sort of parameterize this thing directly. You want to parameterize like individual layers here because you can show that posterior has this form. So you don't sort of need all of that. You just need these individual guys here. And actually as well, what turns out is that when you do this, you're passing you're going from X to U when you're doing this because you essentially start with X and you're sampling a sequence of U's. The way this works out is that you actually pass your X and your sampled U's through the same bijections that you parameterize as part of the model. So essentially it kind of naturally induces a weight sharing scheme between the forward model, which is this thing up here, which has normalizing flows, these families of normalizing flows built into it. You sort of share those same flows in the inverse direction as well, which is kind of nice. People have spent, I think, people have been quite interested in finding ways to share weights between the forward and inverse direction of like a VAE. And this is a very natural way to do that. The Fs are sort of exactly the inverses of the ones that in this forward mode we kind of use to actually obtain the sample spin, which is kind of nice. Cool. So what does this actually get? Intuitively, like having this extra flexibility allows these continuously indexed flows to clean up sort of mass that you would ordinarily misplace. That's sort of intuitively the idea. We have some propositions that sort of under some mild assumptions, you can show a SIF can kind of like recover the same support as the target density, even if you don't have a homeomorphic noise distribution, and perhaps even under a stronger condition, you can actually recover the true data generating distribution exactly. This is really more qualitative, I would say, give a flavor for potentially how this can help. We don't expect these necessarily to hold in practice, but it's kind of interesting. This flexibility does something. And there's sort of an interesting relationship then in terms of continuously indexed flows in relation to both normalizing flows and VAE. And this might be of interest as well, having learned about just normalizing flows and VAEs separately. So essentially, normalizing flow you can kind of think of as like you have some noise, you have some U and it does nothing. It just sort of sits there. There's no impact on the X. A VAE you can think of essentially as you have some noise Z, but you also have a U here, but it's independent from Z. And this is maybe slightly confusing notation because typically in VAE notation, U here would correspond to the latent variables. So U would be normally denoted as Z in the VAE.
That would be epsilon, I guess.
Yes. Because indeed, so you have the reparameterization trick is all about using a bijection to map some fixed noise distribution into X space. So it depends on some additional noise, but in the case of like a Gaussian VAE, you would sample an epsilon, which is normal 0, 1. You would sample some, latent variable, maybe from a normal as well. And you would map this through a you would map that through a neural net, and you would use this thing to, that would kind of rescale where that ends up, and that would give you sort of your sample, essentially. A continuously indexed flow kind of like interpolates between these two extremes. So essentially it's the same deal, except that U is now allowed to depend on Z. That's kind of the idea. And what we kind of think happens, this is a bit loose, but I think there's some truth to this, which is it sort of allows the model to kind of interpolate between cases where like inference is really hard, and it interpolates between inference being easy and expressiveness being high. So in a sense, like a VAE is a very expressive model. It's a really powerful sort of mixture model. You can sort of imagine if you have a sufficiently powerful neural net and you're willing to kind of like take a big enough mixture, which is essentially what a VAE is doing, then you can kind of really get any distribution that you want. But inference on that might be really difficult. Normalizing flow, on the other hand, inference is really easy because it's invertible. So you know exactly which Z gave rise to which X. But expressiveness is sacrificed because of this by-Lifshitz problem. And SIF kind of has the ability to compromise between the two. So you could express your target invertibly, like without, if it does have the same support, essentially the SIF could learn to just ignore this U and just make use of a normalizing flow, just map that through. And then inference is really easy. The elbow becomes tight. This thing actually matches this thing actually matches the posterior, and it all works out. But in cases where maybe that's harder, like in cases where you actually do need some non-kind of diffeomorphic behavior, you have the flexibility to do that, and you pay a trade-off in terms of having to do a little bit of inference, but potentially less than if you just use the VAE directly. That's kind of the idea. Here are some examples of what this does. So these two at the top were kind of where we were, like what the residual flow is doing just by itself. When the same model is combined with a SIF, you can see it really does clean up where the densities place mass. We were careful to sort of make sure it's a fair comparison. So like we did experiments where if you're adding stuff with SIF, right, to a normalizing flow. So you're adding like additional these P of U given X's. And you have to add the variational approximation as well. So you're adding more parameters, it's a bigger model, but we made sure like we tried a bigger residual flow as well to check, and it's kind of the same behavior there.
Just to that point, should I think of U as being as big as Z typically?
I know, so it would typically be really small actually. So it definitely doesn't need to be, yeah, that's a great point. So Z obviously needs to be the same dimension as X because these need to be invertible. But you can be like 10 dimensions or something. Yeah, and that gives you actually quite a lot of control over how much more you're adding to your sort of baseline kind of flow model. But yeah, basically, regardless of how big we made this, as the theory predicts, you can't make this work. But with a SIF, it does clean it up. Here are some more examples kind of showing what goes wrong. So like, again, you kind of see, so the top here, this is a MAF. So this is the second of those architectures that I gave earlier. You kind of see that it's having problems separating out. Like this is all one connected component here. Like there's separate modes here, but essentially because the base distribution it's starting with is a Gaussian, it sort of can't separate that out, and it has to just kind of squeeze everything to mostly follow where the mass lives. With a SIF, you get much more kind of well-behaved.
Huge difference between layers. So 20 for MAF,
yeah.
You're using 5.
Yeah, so that's another, yeah, absolutely. Yeah.
That's huge reduction in parameters, I guess.
Yeah. It's not as big as it might seem because there are these extra components, but yeah, we definitely were able to get, we were able to do better with less actually in the end, in many cases. And we think because of this homeomorphic problem, like this,
I guess you have the same result for IF as well. Like if you use this like on the other way around, I think so. Yeah.
Yeah. So
that's quite a huge reduction of layers. Yeah.
Yeah, absolutely. It's because there's sort of nothing like it was. Yeah, and it becomes unstable with 20 layers as well. So
yeah.
It's not all perfect. Like this is an example where it didn't quite fix the problem. I would claim that this is better than that. This is like normalizing flow. This is like the same baseline flow but supplemented with a smaller SIF model. It does better, but it also doesn't quite get what you want. But what we found then is just if we did make the model bigger, the SIF model bigger, it actually eventually capture the target. Whereas this one up here, it actually became more unstable as we added layers.
One question, I mean, like for the MAF, you have to kind of do that permutation layer because it's reactive to the ordering. for SIF, you also do permutation because, I mean, like, does it react to the ordering of the variables?
What do you mean by the permutation?
I mean, like, for example, like, I have like a X, but like I can reorder the dimensions, right? And so that would change. So if I do not, I mean, like in math, if I have like 20 layers, within each layer, I'll have kind of change the ordering of the dimensions, like which is dimension 1, and like that's what's used kind of you have to use for this type of.
Yeah, so I don't remember what we did.
Because I mean, like vaguely, I remember like for like there's some argument about uniqueness, like it has to be like a unique map from one space to other. So like, obviously it's impossible to find a unique map. So some tricks is like you kind of make it kind of change the dimensions arbitrarily some way.
Yeah, so I don't, let's follow up on that. I'm not sure, basically. So I don't believe we had to do anything like that. As I recall, I mean, because if I might be misunderstanding you, but if the way I'm thinking about a math, like you just pass, like you don't have the same dimensionality.
But I'm saying like the y-axis and x-axis in that 2D,
Yeah.
like in your SIF, that y-axis in the first layer would be the y-axis in the last layer. So you don't have to swap the axis.
That would be real MVP though, where you
Yeah.
if you don't have to do that necessarily, because well, I guess actually you might still want to.
Yeah. In math, you
Yeah.
always do that because then there's if you don't do that, there is loss of performance.
Right.
So I was just wondering whether you do that.
Yeah, okay. So yeah, absolutely. And yes, and I think the answer is yes, we did. So what we did is we inverted, we implemented permutation layers.
Yeah,
Like another
layer, yeah.
It's a normalizing flow that's not a very expressive one, but it's still invertible. But we had, I think pretty much in all cases, what we tried to do is keep it like for like.
Yeah.
So it's not going to be perfectly like for like because there's a discrepancy between the layers. But I think any case where we had like something like a permutation layer between math layers, we reproduced that for the SIF as well. Yeah. Just made it smaller. Yes, I do. Yeah, I do know what you mean now. Cool. And yeah, so we did this on image experiments as well. Here's an illustrative example using some relatively high dimensional data. Essentially, this is doing density estimation for MNIST and CFAR10 image dataset. The unit here is bits per dimension. You don't need to know what that means, but lower is better. So, and we did best. Again, we sort of made sure that we had a fair comparison. So we had kind of like a small flow, which is sort of the baseline flow inside the SIF. We then also trained that separately just without the SIF to see how that does by itself. So adding the SIF certainly does better than the res flow, the small res flow. But then obviously that adds parameters. So we tried adding more layers to the res flow and see and saw what we got and fix the problem basically. So it is an improvement in this case to use our architecture. And this wasn't just this problem as well. We tried other data sets. Great. So that's the end. I'm sure you're all relieved because it's the end of a long day, but thank you very much for listening. This is also joint work with various collaborators. And yeah, any of us do reach out if you're interested in to any of us. And yeah, we'd be very happy to speak more. So yeah, thank you.
I was wondering about like the Lipschitz thing. I was just wondering like it's valid for continuous time flows as well, because my intuition is that let's say I have an OD, that's my flow, right? Like I now we know that we can produce chaos, right? So if I have like a chaotic OD starting from like